In this video, we will discuss about relations and functions in that equivalence relations. But before going to that, we shall recall some of the things we have studied in the first PUC. One thing is Cartesian product, which is if A and B are any two non-empty sets, then the Cartesian product of A and B is denoted by A cross B and is given by A cross B is equal to set of all ordered pairs AB, where the first element A belongs to the first set and the second element belongs to the second set. Now if we take an example, like if A is equal to the set ABC and B is the set 1, 2, then the Cartesian product is given by, see, we can do it like this. Here A should be related to both the elements of the second set, which is 1 and 2. They are the ordered pairs A, 1 and A, 2. Similarly with B, B1, B2, and with C, C1 and C2. Let's also recall what is a relation is. As we know, a relation R from a non-empty set A to a non-empty set B is a subset of the Cartesian product A cross B. The subset is derived by describing a relationship between the first element and the second element of the ordered pairs in A cross B. The set of all first elements are called domain and the set of all second elements are called range of R. Now coming to the actual topic, which is equivalence relation. First, let us see what is an equivalence relation is. A relation is said to be an equivalence relation if it follows the following conditions. First condition is called as reflexive, which means the same element, the both same elements should be belong to the relation for all A belongs to the given set. Symmetric means if AB belongs to R, first and the second set belongs to R, then the reverse of it, which is B, A, that also should belong to R. And the third condition, which is called as transitivity, if AB, one order pair belongs to R, and if there is another order pair BC belongs to R, then that should imply AC, the first element of the first set, and the last element of the second set must be in R. This is called as transitivity. If all the three conditions are satisfied, then the relation is called as an equivalence relation. Now, to understand this, let's see some examples. Let me take a simple example first. Let us think that there are three friends. We can name it as Amar, Akbar and Anthony. This is Amar, Akbar and Anthony. Now, what is reflexive is? As I told you earlier, reflexive has only one element. So, Amar must be related to Amar. So, let's take a relation. Now, let's take the relation as the first letter of the names are same. So, when you see Amar with Amar, obviously first letter of Amar is A and we are taking Amar again. So, first letter is A. Of course, all the letters are equal, but we are bothered about only the first letter. So, this is called as reflexive. So, we can see this. Amar has the same first letter as Amar himself. So, the relation is reflexive. Now, what is symmetric is? If Amar is related to Akbar, then we must have Akbar is related to Amar, which is true in this case because Amar's first letter is A, Akbar's first letter is A. When you reverse it again, Akbar's and Amar's both has same first letter A. Now, what is transitivity? The condition says if Amar is related to Akbar and if Akbar is related to Anthony, then Amar must be related to Anthony. Of course, this is true in this case. Amar has first letter A. Anthony also has first letter A. So, the relation here is transitive. Now, let's take some more examples which is there in the textbook. Let T be the set of all triangles in a plane with R, a relation in T given by R is set of all congruent triangles T1 and T2. We have to show that R is an equivalence relation. What do you mean by congruence triangles? Congruent triangles means if there are two triangles with the corresponding sides are same and the corresponding angles are same, then they are said to be congruent triangles. How to take it? As we know, R is reflexive because every triangle is congruent to itself. If you take the same triangles twice, obviously they have same angles and same sides, corresponding angles and sides, so that must be equal. And if T1 and T2, if two triangles which belongs to R, then obviously T1 is congruent to T2. If T1 is congruent to T2, obviously T2 must be congruent to T1. The reverse should hold good. Therefore, R is symmetric. Now, if you take three triangles T1, T2 and T2, T3 belongs to R, what is the meaning? Obviously, T1 is congruent to T2 and T2 is congruent to T3. In that case, T1 must be congruent to T3 because these two are congruent, these two are congruent. So obviously, first one and third one is congruent. So T1, T3 also belongs to R. Therefore, R is transitive. So we have all the conditions satisfied: reflexive, symmetric, and transitive. Therefore, R is an equivalence relation. Now let's take one more example. Let L be the set of all lines in a plane and R be the relation in L defined as R is set of all lines L1 and L2 where L1 is perpendicular to L2. You know the meaning of perpendicular. If two lines are perpendicular, the angle between them is 90 degree. Now we have to show that R is symmetric but neither reflexive nor transitive. Now look at this picture. I have taken three lines. This is L1, L2 and L3. Here you can see that R is not reflexive because a line cannot be perpendicular to itself. Obviously, a line is parallel to itself, but it cannot be perpendicular to itself, though R is not reflexive. But of course, R is symmetric because as you can see, if L1 is perpendicular to L2, L2 is also perpendicular to L1. Therefore, R is indeed symmetric, but R is not transitive because if L1 is perpendicular to L2 and if L2 is perpendicular to L3, then we know that L1 is parallel to L3, not perpendicular to L3. So in that case, R won't be transitive. As you can see, L1 is parallel, so we cannot have it as transitive. Let's take one more example. The example says, show that the relation R in the set of integers given by R is equal to set of all ordered pairs AB, where 2 divides A minus B. We have to show that this is an equivalence relation. Now, to show the reflexivity, R is reflexive because, as you know, 2 divides A minus A. We have to replace second element by the first element itself. A should be related to A itself. So, if 2 divides A minus A, that means 2 divides 0. We know that A minus A is 0, which is true. 2 can be divided by any, 0 can be divided by any number. So, 2 divides 0 is correct. So, this holds good. Further, if AB belongs to R, then obviously the meaning is 2 divides A minus B. We have to see the reverse. Therefore, 2 divides B minus A also. Hence, BA belongs to R. As you know, if 2 divides A minus B, the reverse also holds good, so which is symmetric. But when it comes to transitivity, if AB belongs to R and BC belongs to R, then A minus B and B minus C are divisible by 2. Now, A minus C can be written as A minus B plus B minus C, where B get cancels. We are left out with A minus C. So, that's what we wanted. So, 2 divides A minus C. So, that shows that R is transitive. Therefore, R is an equivalence relation.